Awesome. Okay, so this is our last class before our first exam. Our first exam is going to cover units 1.1 all the way to 1.7, but 1.1 doesn't really have any information. So 1.2 all the way to 1.7. So this class included in this exam. I know that this material will be fresh, so maybe I won't be asking you the harder questions, but I could definitely still pull from these questions. If you are ready to start studying, so I'm hoping by right now, you've completed those quizzes and you've completed the homeworks. That's the goal. If you haven't done that yet, make that your goal in the future. Like it's 2 days in front, be done with everything because now we want to start honing in on how we prepare for the exam. If you're on the other side of it, get everything done by today so you have tomorrow to hone in those skills. If you are doing those homeworks tomorrow, you're not exactly studying for the questions on the exam. It won't be as helpful. So yeah, get those homeworks done because those will all close at noon on Friday, and then you have no other option. You can't open them up. The quizzes are really helpful to help prepare for the exams because I ask very similar questions where the homeworks are going to be harder than the exam. Help you prepare, but they're not exactly the questions I ask you. So as you start getting ready for an exam, you want to be looking at questions I might ask you. Those questions are in the resources module under exams from 2024. There are 4 exams in that module. Our first exam is going to be exams 1 and 2. If you only study exam 1, it's not going to be enough. There are several questions on exam 2 that are going to be what we cover. And I have them highlighted here so I can show you what those questions are. But don't just look at exam 1 because they had 4 midterms. Y'all have 3 midterm exams. Are there any other questions about that before we get started? Okay, let's get started on chemical equations. This is section 1.7. I do have a worksheet that we'll work on towards the end. And then I did offer for the students, if y'all would like to continue working through the practice homework, or so the practice exams, I will just stay on a little bit later today to go through some of those questions if we run out of time. But you're welcome to stay if you need to go, no worries. So with chemical equations, our goal is to write balanced chemical equations. Majority of the time when you're asked a question, they're nice enough to balance it for you. But when you're still learning how to like even make sure everything is going well, you want to make sure you know how to balance them. So sometimes with these problems, you'll be asked to balance them. Whereas when you get past this section, typically they'll give you a balance. I do want to point out that we want to do micro, macro, symbolic. Those balanced equations, if I write it all out, that would be a symbolic representation of the chemistry going on. Whereas the macroscopic, let's say I was to do a combustion reaction, the chemical equation would just be like gasoline and lighting it on fire. So macroscopically, I'm seeing a little mini explosion. The particles would be the fuel breaking up into its individual components and combining with oxygen to create products, typically carbon dioxide and water. So that would be microscopically, and then symbolically are those letters that be put on. And I'd love for us not to just always memorize the letters and the numbers. We want to think about what's really going on macroscopically. Here is a great image that kind of includes everything. It shows macroscopic, it shows microscopic. I don't see symbolic, but it's a great picture. When we think of matter, it includes pretty much everything, any substance. There are pure substances and mixtures. So pure substances is what we've seen so far. Essentially, if I was to have a glass of only water, which is what I have right here, my glass of water, it's pure because the only thing in here is water. Even though water is H2O and it's a combination of 2 chemicals, it's still pure because it's all one compound. If I start mixing things in, like I want to go play tennis, so I'm going to add some electrolyte in here. Now I have a mixture. It's no longer pure because I have water with dissolved electrolytes. If it's dissolved, that's okay. It's still going to be a mixture. If I go into the 2 differences between pure substances, you have elements. So elements would be like if I had a solid block of gold. I wish. But if I had a block of gold, that is a pure element all by itself, 100% only gold particles. Whereas the water is a pure compound because H2O, it's 2 different elements combined but it's the only thing in here. So it's still gonna be under pure substances as a compound. So compound versus pure element. I'm going to review because I did see some of these questions on the practice exam. On day 2, I talked about certain compounds are diatomic, meaning that the only way they exist as a pure element is connected to itself. That's what we call, Dr. Patterson calls Brinkelhoff. So let me do it. You write bromine, I think that's Brinkel. Iodine, Brinkel, nitrogen, oh, oxygen. That's out of order. Brinkel. I don't know what the L stands for. I know it's into, I already did into, O2, A2. That might, no, fluorine would be the off. There are certain compounds, I think that's all of them, but I know I'm not spelling it right. I'm not a good speller, that's why I'm a chemist. There are certain elements that they exist naturally outside, but they have to combine with each other. So just because it's the same element just twice, it's still going to be considered a pure element because it's only one element. So here we have gold, which I think is AU. Just a solid block of AU. Wait. Yeah, okay. AG is silver. I kind of got that flipped in my head. This is a solid block of AU, it's pure element. If I was to just have hydrogen gas, it's still a pure element from hydrogen. It just exists combined. On the other side of things, in mixtures, there's a difference between the mixtures. There's homogeneous and heterogeneous. And the way that I think about these is you can use those prefixes to kind of determine between them, homo versus hetero. Homo means it's the combination and it means the dissolution. If I was to let's say I want to make sweet tea and I dissolve a bunch of sugar in my tea, if it's dissolved, it's a homogeneous mixture because all of that solid sugar is now in the liquid phase. Heterogeneous is if I was to mix sand in water. There's no way sand can mix in that water. So it's a heterogeneous mixture because they don't dissolve into each other. Okay, so if it is a homogeneous solution where it's all the same phase, then yes, that would be a homogeneous mixture. Heterogeneous, it's just solid liquid, liquid gas, I don't know. If you mix oil and water, they stay separate, right? So that's going to be a heterogeneous because it's not exactly coming together. So here are those macroscopic ones versus is this microscopic or symbolic? The middle. Microscopic because it's particles, not letters. Okay, so great job. All right, let's talk about those phases because I was kind of hinting at them. When I think of a chemical phase or a physical phase, I'm just talking about solid, liquid, and gas. So water is probably the most popular one. So if you can pretend this is water, I think that's the easiest. We learned about the life cycle of water when we were in elementary school, which I still think of that when I think of this. I still do. I love it. So water, it's always going to be, we kind of think liquid phase. If I was to go from liquid water to solid water, what process is that? Freezing, yes. So if I go from liquid to solid, it's freezing. If I go from solid to liquid, let's say I have ice and it goes into a liquid, what's happening? It's melting, yes. So if I go from solid to liquid, it is melting. All right, another one is if we are going from a liquid to a gas. Let's say I want to boil some eggs. So I am going to put some water on the stove and I'm going to set it to a high temperature. But over time, my full pot is now maybe half the amount of water, liquid water. What happened? Yeah, some of that water turned into a gas. And so that phase change would be evaporation. So it's going from a liquid to a gas. So evaporation, and then they have vaporization here. There's always gonna be a more chemical term for it, but you're absolutely right. Now, let's say, I want to get that water to come back into a liquid. So usually it's what you see if you were to have like a glass and what's happening on the outside, the glass is really cold. What do you think that is? Yeah, a better way of me saying that is if I was in a very humid room and the windows get very foggy, what's happening is that water, there's so much water in the air. The water is the liquid on the windows. So that's condensation. So that's going from a gas to a liquid is condensation. If I was to start playing around with this and start giving you different chemicals, let's say I'm going from carbon dioxide from this phase to this phase, it's the same thing. But if you're like myself and I'm like, well, I want to remember it the easiest way possible, I always think of this water. Now, there is a such thing as going from a solid all the way to a gas. It's less common because it's very hard to do. You have to have a very specific temperature and a very specific pressure, but going from a solid to a gas is called sublimation. This is what my favorite one example of this. If I wanted to really cool the things in my ice chest down, but I don't have a lot of time, and I know that my ice chest, if I put ice in there, it's gonna melt all that ice super fast. I'm gonna go to HEB and I'm gonna go and buy a bunch of dry ice. Does anyone know what dry ice is made of? Not liquid nitrogen, because liquid nitrogen, I think it's a lot colder than dry ice and it's more dangerous. So it's actually solid, because it's dry ice, solid carbon dioxide. Yeah. So what happens is when that dry ice, if I was to take a big block of it, don't ever touch it with your bare hands. It will burn you because it's like a negative 70 degrees Celsius or Fahrenheit, very cold. And it just because it's cold, it can still burn you. If I take that solid block of ice and put it out in this classroom, you'll start seeing a bunch of fog come around it. That's because that solid block of dry ice is turning into carbon dioxide, completely skipping the liquid phase. That's sublimation. And then going from a gas to a solid, I'm not sure which one this would be. A lot of the times, if I was gonna do this, you just said it, liquid nitrogen. Nitrogen is very prominent in our air. So what they would do is if they purified nitrogen, they would probably take it and pressurize it to a very specific temperature. And they can get that nitrogen to get down into a solid, but it has to be very, very, very cold. Whereas like even negative, I think 100 would be liquid state, not solid. So it needs to be very, very, very cold. That would be deposition. These are under very, very specific circumstances, not very common. I don't expect you to have them memorized, but what I do want you to get comfortable doing is if I start saying phases where I have solid, liquids, and gas, I just want you to identify what's going on macroscopically and microscopically to those particles. But this is a little picture that shows it. So just know temperature. Let's go back to water. Does anyone know what temperature in Celsius does water go from a solid to a liquid?
0 degrees.
0 degrees? What about Fahrenheit? 32. Does anyone know in degrees Celsius, what temperature does water boil or evaporate? 100. I think it's 212. I might be wrong for Fahrenheit. So you can see that there's a trend. So going from a solid to a liquid to a gas, the temperature has to increase if it's under standard conditions. Because I can't, if I'm in the room right now at this temperature with no energy being added to it, it will never turn into a gas. It's not hot enough. For me to get this amount of water to turn into a gas, I have to add energy in the form of heat to get it to turn. So temperature is definitely important. Now, if I put it outside in the Texas sun, some of that will definitely evaporate because that top layer is getting hot enough. Let's review. Which figure represents an element, compound, or mixture? So to me, the easiest one is element. Which one is purely one thing? Just because there are two things attached, both of those things are the same. So this would be a pure element. What about a compound? A, yes, A is a compound because there's more than one element in it, but it's all the same thing. And this is what I like, even if you don't remember what a mixture is, you did process of elimination and whatever is left over has to be mixture. That's my these exams. When I have a very high test anxiety, but until I taught myself process of elimination, like that's why some students who are really, really good test takers, they might not know the material, but they're really good process of elimination. So if you ever don't know how to answer this, this is my favorite thing about chemistry is bullshitting. Use your process of elimination to figure out what's left. So I'm confused by this. I have no clue what's going on, but it has to be what's left over. That's a mixture. And then just review, a mixture is a combination of more than one pure substance. So I have this and I have this, they're all in solution together, therefore this has to be a mixture. Is this a physical or a chemical change? This in depth, a physical change does not affect the substance. If I take water and I freeze it, it's still water. It's still H2O. Water is still water in the gas, liquid, or solid phase. It's always going to be water. So that's a physical change because I'm changing the phase. I'm changing the physicality of it. I'm not changing the substance itself. If I was to add sugar to it, maybe that would be changing things. But water is always going to be water, whether it's this phase, this phase, this phase. So keeping the chemical identity or composition. Oh, maybe I was just wrong. So if I did mix sugar in, it's still going to be a physical change because it's still water plus sugar in solution. Now, a chemical change would be something that is changing the composition of your chemical. So combustion reactions. If I mix a fuel with oxygen and it explodes, I am not having any more of that starting fuel left over. It's all gone. It's been turned into carbon dioxide and water. That's a chemical change because it's not original material here. Now it's just carbon dioxide and water. So that would be a chemical change. So if I burn something, like if I burn wood, ash is not that original wood material. If I corroded something, rust. If I take a pure piece of iron and then I waited a year while it left outside in a very humid area, it's now rust. It's not going back. You can try, you can to remove the top layer, but it's very different. It's a chemical change. That original rust will not go back to iron. The only way to fix it is to get it off. I don't know if I've ever dealt with tools. I always get really mad at myself when my tools get rusty, but I have to literally like get it off. Or I do a very big chemical bath. That'll help too. But I'm changing the composition. I'm not, the rust is gone. And then reactivity would be like if a reaction happened and then completely change the products. So I do want to point out, I love when I include pictures like this because it challenges your ability to understand the microscopic sense. So I want to point out that these compounds in both these pictures are the exact same. Can y'all see that? But one picture shows it in a liquid state and the other picture shows it in a solid state. How do I know that? If this was oh, go ahead.
Oh, I was gonna say.
Yes, so one's more fluid, but so is gas. Gas is pretty fluid. How do I know that's not a gas? 100%. Gas will fill the volume of the container. So if this was gas, those particles would be everywhere. But since this is kind of fluid, but in one area, that would be a liquid. I know this is a solid just because it's a nice, pretty structure and it's all pretty. The structure is the best word to term for it, but it's pretty structured and it's all in one spot and it's not fluid at all. That's definitely a solid. So this is a phase change, and that's why it's a physical change going to a solid. This microscopic picture shows a gas. I can tell they're both gases because they're filling the vessel. But in this one, I have, let me use color. I have 5 green plus 5 black. And on this one, I now have 5, I'll just do GB. So I don't have just green or just black anymore. I have a combination of it. So it's a brand new chemical, and that's why it's a chemical change. Okay, so I can ask you this picture or these questions based where I give you, let me show you. I can give you a symbolic Sorry, I think it's coming up. This would be a symbolic way I can ask you in multiple choice. I can say, I can give you a list of these and I say, which one's the physical change, which one's the chemical change? That's a symbolic way. But I can also ask with pictures and say, which one is a chemical change versus which one's a physical change. So I love that. If you take Gen Chem, they'll also ask you those questions. All right. Y'all answer this one, okay? So when you're ready, this is how we do it in Gen Chem. If you think the answer is A, you do a 1, but don't do it here, do it here. If you think it's B, do a 2, C is 3, D is 4, E is 5. So what do you think? It'll go away in a moment. If you are confused, use the elimination process. At least get it down to 2 answers and then make an educated guess which one's more right. Which one do you think wrong? Which one's not a chemical change? A. So H2O going from a liquid to a gas. Oh no, that's a solid. That one is definitely not right because that's a physical change. Any other one? E. H2O going from a liquid to a gas, okay? C is giving you that keyword. It's using the word melting. Melting means it's going from liquid to a, or solid to a liquid. So that little like key word tells you this has to be a physical change. So I'll just use butter. I'm going from a solid, but it's still butter. Okay. But now we've given ourselves a 50-50 chance of getting the right answer. Which one do you think's more right? Absolutely. So I'll tell you why CE is not correct, but this is a great way of giving yourself a good shot on an exam. So D will be the right answer because iron to rust, which is iron oxide, is a brand new chemical. So Fe, you do a different color. Something like that. That's a brand new chemical. That is absolutely a chemical change. I don't know if that's what the iron oxide looks like. I don't know what the balance, whatever. It's just iron plus oxygen turns into iron oxide. But sugar dissolves into hot coffee. Sugar is going from a solid to a liquid. It's a mixture, but the sugar is still sugar. That sweetness you taste in coffee is not a brand new coffee compound. You're just tasting the liquid sugar that's added to the coffee. But it's okay. When I read this too, I'm like, well, is sugar truly changing? But then I thought rust is definitely a chemical change. It has to be D. So why waste my time thinking about E? Does that help? All right, any questions on that? And then if you are someone who takes a long time on exams, if you learn this process and like you can eliminate things, you don't even have to waste your time trying to confirm, well, it's E. E could be right. No. Just circle the right answer and move on. Skip that next step because if you don't have enough time, at least you've saved some time here. So it's a great way to take exams a lot faster. All right, chemical or physical change. I was hinting at this on the previous slides. If I was to give you this one and ask, okay, I have A and B. I'm not always so nice. I might give you C and D and E, but which one of these is physical?
The first one
Why?
is going to the solid.
Water is not changing. It's still water, regardless if it's a solid or a liquid. What about B? Is it physical or chemical? Yeah. Why? Yeah. So what is water if it's H2O? But if I break it up into its components, hydrogen gas and oxygen gas, hydrogen gas is not quite that safe for us, but oxygen, awesome. Our bodies require oxygen. But if I was to have like, let's say, a room of pure hydrogen gas, we would all die. So it's not the same thing as whereas if I had a room full of water, we could at least hold our breaths, but we would still die. But it's not gonna kill you the same way as if we were breathing H2 gas. But yeah, it's a brand new component. Hydrogen gas and oxygen gas are not water, so it has to be a chemical change. But I like this question because they're using the same elements and they're really challenging your ability to recognize the difference between those two terms. Stop me if y'all have any questions. You can blurt them out. You don't have to raise your hand if you don't want to. And then same in the chat, please ask questions if you have them. This is going back to, I think we did this in day one. I think it was day one. We need to make sure we know how a chemical reaction looks. Here is a combustion. Ooh, what chemical is that? So bute is 4. So 4 carbons. So yes. So let's go through alkanes real quick. So alkanes, if it's 1 carbon, it's methane. What about 2?
Ethane.
Huh? F, right? Ethane.
Okay.
3, propane. 4 is butane. 5, and so now it gets easier. Once you hit 5, it's regardless. So 5 is pentane, hexane, heptane, octane, nonane, decade. But the first 4 are the hard ones: meth, eth, prop, bute. So because there's 1 carbon here, that's methane. Okay. So the chemical formula, when we start balancing things, I do want to point out the chemical formula, we're going to be messing with that because then you're changing the reaction itself. When we balance things, we're just changing the amount. So that's prefix. No, coefficient is the word for it. The coefficient, put this out. This is a coefficient. That is what we're changing when we balance reactions. So we're not changing the substances. So Dr. Patterson recommends, like, before you're comfortable with this, just put a box to tell yourself, no, don't mess with it. Where we'll play around with the numbers out front. If there is no number out front, what number is it? A 1. Because, okay. I also want to point out a few things. The law of conservation of mass. It has to be balanced. If I have 10 hydrogens on one side, I have to have 10 hydrogens on another. The physics laws, even though I hate physics, they're not going to be, it's not a miraculous thing we're doing in this class. It has to make sense. So if I have it on the one side, I have to have it on the other. You might hear me use the word reactants and products. Reactants are what you add together. Products are what you, so if you hear me say that and you're confused, raise your hand. Like sometimes we'll skip steps, but reactants are on the left side, products are on the right side. And then I love this, Dr. Patterson, she's a big nerd. I love her so much. So it's like we're disassembling and reassembling Legos. So in a combustion reaction, everything that you have in the fuel will break up into its parts and combine with the other thing. So if you notice on the left-hand side, carbon attaches to oxygen and hydrogen attaches to oxygen. So it breaks up and then attaches it to the oxygen. That's what's happening over here. So reminder, subscripts are what is the number after the element itself to tell you how many are attached. So if I have this is H2O. I have 2 hydrogens attached to an oxygen. The coefficient tells you the amount. So, sorry, my phone's blowing up. All right, no emergencies. Sorry. It's hard to separate yourself from a phone when people just call you out of nowhere. How do I know that that 4 is correct? Count the number of molecules. That 4 tells you the amount of a substance. I can't say this is, let's say this is, there's H8O4. Why is that incorrect?
That would mean that they're all part of one molecule.
Exactly. We don't have a bunch of oxygens attached to hydrogens here. That just does not make sense. We have individual H2Os and there are 4 of them. So the coefficient tells you the amount of them, and then that's why we do not want to play around with this. So if I tripled this, I would now have 12 H2O, but I wouldn't be changing it to H24O12. I wouldn't be doing that. Amount can mean a couple of things. We're gonna get into this in unit 2, and we'll harp on this a lot more when we're back in actions, but no worries at memorizing this now. It's all about ratios. So if I was to just say it's an amount, so molecules versus moles, moles is the term in chemistry that represents an amount of something. So it's either 4 molecules or 4 moles. As long as you're consistent and saying that's molecules, 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 then it's fine. Ratio between them. So let's talk about an equation. This is a nice equation that tells you a lot of things. It's the Haber process. It's how we create ammonia that it could be turned into a liquid that we use for chemical cleanings and stuff like that. But this is a very popular thing that we use in chemical industry. So this equation tells us a lot. First, we know the identity of our. So I have H2, I have N2, and I have NH3. Those are our chemicals. Next, it tells us the ratio. So 1, check if it's balanced. Shoot. Are there the same amount of hydrogens on both sides? How do we do that? First, we'll do that in a little bit, but we'll skip that. We'll skip that for now. So we'll do that on the next slide. We'll check how much, but coefficients are also going to be important. So if I have a 3 here, I assume there's a 1 here, and then there's a 2 here. That tells us the ratio. So I have 3 molecules of H2. Let's say these are H2. I have 1 molecule of N2. And then I have 2 molecules of NH3. So let's see if I can do that. So that's how I can kind of confirm I have the same amount on both sides. On the left-hand side, I have 6 hydrogens. On the right-hand side, I have 6 hydrogens. On the left-hand side, I have 2 nitrogens. On the right-hand side, I have 2 nitrogens. So this is a balanced reaction, and I can see those coefficients mean the different molecules. Physical states. You'll now start seeing physical states being given. They're not always going to be important to the question you are answering, but sometimes they are. So G, what does G stand for? Gas. L for liquid, S for solid. Now, aqueous, same as liquid, but aqueous. What do you think of aqueous when I say aqueous? What solvent or solution is it dissolved in? Water. So it's still a liquid, it just means it's dissolved. It's like if I take sugar, solid sugar, and I dissolve it in water, it's now going to be sugar aqueous. So it's still a liquid, but it's just dissolved in water. I think the only way for me to dissolve it and like make it a pure liquid is if I heated it by itself to a really high temperature. All right, gas. Sometimes there are going to be special conditions where they might say they added heat. They can say they added light, catalyst, reagent. Obviously, that's going to be more advanced chemistry, but the reaction might tell you. So if I look here, higher pressures and higher temperatures, that's how this reaction is coming into play. They had to heat pure hydrogen gas and pure nitrogen gas at very high temperatures under very high pressure to get ammonia. So you can learn a lot from the reaction that they give you. So yeah, sometimes I can ask you a bunch of questions about it, but a lot of this is more for more advanced chemistry, but it's great. let's go through some rules with balancing reactions, because we're gonna pretty much reactions the rest of the class. Write the formula for all of the reactants and products separated by a plus sign or an arrow. This is the step in which you should write subscripts. If you know it's a certain chemical, write those subscripts. As you're a beginner, draw a box to remind yourself not to mess with those subscripts. You don't need it, you really don't. But if you find that you keep making this mistake over and over again, Dr. Patterson does recommend putting a little block for yourself to say, don't touch. So she draws a block around it and says, okay, I can't mess with this. I can only mess with things out front. So we'll do both. Pick an element to start with. Try different coefficients until you have the same number of atoms or the element. And then this is something that I always remind myself, save the pure elements to the end. Those are the easiest to balance. If you do it in the beginning, you might mess everything else up. If it's odd, it's sometimes very hard for you to balance odd numbers if they are diatomic. So sometimes you need to just double everything. So you need to play around with those numbers if it's an odd. But sometimes if it's by itself as a 1, odds are fine. Repeat it until all elements are balanced. Okay, so this is a really good check sheet for as you're balancing. Let's practice. So previously, don't try to ignore the numbers that we had out front. You might be asked to kind of create a balanced reaction on a sentence. And the worksheet I gave you does do that. In the Haber process, nitrogen. So nitrogen is a Brinkelhoff. It does not exist by itself. It wants to be in 2. I don't care about the phases. I don't care because it didn't tell me the phases. I don't have to make assumptions here. Nitrogen reacts with hydrogen. Hydrogen is also a Brinkelhoff. It does not want to be by itself. It's going to be H. The same amount. This is kind of how I was taught in General Chemistry 1. If you are very mental and you want to do this in your head, that's fine, but I'm not mental, I'm jealous. But I tend to, like, under the arrow, write the elements that are on both sides, and then I'll count. So on the left, I have 2. There are 2 nitrogen, right? On the right, I have 1 nitrogen. So I'm assuming there's a 1 because there's no subscript after the nitrogen. Does that make sense? Okay. For hydrogen, I'm going to count. I have how many hydrogen are on the right? 3. So I need to make sure all of this gets balanced. I'm going to start with the nitrogen just because balancing this is the easiest. These are pure substances over here. You save them for the end. So I want to get the nitrogen to be a 2 over here. What do I have to do over here to get the nitrogen to be a 2?
2.
This is when you want to put your coefficient out front. Okay. But so now when I add that up, I have 2 nitrogen, but how many hydrogen? So 6. So you get to multiply this number times your coefficient, because if I have 3 hydrogen for 1 molecule, 2, just double it. So I have 6 hydrogen. Does everyone see how I was able to get 6 hydrogen? Please let me know. So I just took the 3 and multiplied by the 2. All right. So on the left-hand side, now our hydrogen is not balanced. What do I have to do here to get 6? Yes, I can't put a 6 out front because then that would give me 12. So to do that, I need to put a 3. Okay. Double check and make sure everything counts. I have 2 nitrogen on both sides, and now I have 6 hydrogen on both sides. If you don't get this, you can definitely do what Dr. Patterson recommends and put those boxes around to remind yourself, don't touch. I should have done that, I'm sorry. You're only playing around with the coefficients. I'll do that on the next one as I'll box everything up. Yeah, that is a balanced reaction. All right, the next one is a wonderful question that Dr. Patterson likes to ask, because sometimes when you ask what is the balanced reaction, and if it's a homework problem, students will just Google it. I mean, no shame, I always Google to check my answers, but sometimes they will Google without checking. So this is a great way of asking a question to really hone in, because you're not gonna be able to Google this. You have to be able to have the balanced reaction. So we already worked hard. I'm gonna put the balanced reaction that was N2 plus 3H2 becomes 2NH3. So you did it, we did the hard work. What is the coefficient of ammonia when the reaction is balanced? So 1, 2, 3, or 4? Yes. So what is the coefficient out in front of ammonia? If I was to ask, what is the coefficient out in front of nitrogen, what would you say? What if I said hydrogen?
3.
What if I said, what is the sum of all the coefficients?
6.
So 1 plus 3 plus 2, that's 4 plus, yeah. So if I said, what are the sum of the coefficients on the reactant side? 4. What if I said product side?
2.
So she'll ask this question in a variety of different ways, and by she, like, I will pull some of her similar questions on our exam. But as long as you have that balanced reaction, you can answer this question. Because we're focusing on the coefficients.
So when you test, are we gonna have to like know like what ammonia is, like things like that?
I would help you I think, because I don't think that you'd have that memorized quite yet. It never hurts to ask me. So sometimes the student will ask me a question where I'm like, I'm sorry, it seems like you're asking for the answer. But if it's a question like that, I can do my best to help you and say, okay, ammonia is NH3. If I saw that you put N down instead of N2, I wouldn't be able to help you, but I don't mind saying it's NH3. So even if you are confused by something and you think I wouldn't be able to help you, at least ask and give me the opportunity to say, sorry, I can't. Because what happens if I say, sure, I'll help you? That's my advice. Yeah. Let's do this one. Hydrogen has oxygen to make water. So what am I going to write?
Two.
It wants to be combined. What about oxygen? O2 becomes water, which is, why don't I do it like this? Is that water? No. It would be balanced, but it's not water. I'm gonna write underneath my letters, let me do a different color. Hydrogen and oxygen. Those boxes. To remind myself, I don't mess with this. I mess with the number out front. Okay. How many hydrogen on the left-hand side?
2.
How many hydrogen on the right-hand side?
2.
Yes. No worries. How many oxygen on the left-hand side?
6.
How many oxygen on the right-hand side?
1.
So I cannot leave this as is. It is not balanced. So if I want, let's start with the oxygen, because there's no point messing with the hydrogen. If I want the oxygen to now have a 2, what do I have to do to the coefficient in front of water?
Okay.
Okay. So if I do that, I now have 2 oxygen, but how many hydrogen do I have? 2 times 2, 4. So there's 2 hydrogen here, and there's 2 out front. So I doubled, let me write it down. So I went from one H2O to 2 H2O when I added the 2 out front. So the total amount of hydrogen are now 4. So 4. I don't need to mess around with the oxygen because the oxygen's already balanced. But what do I have to do to this H2 to get 4 hydrogen? Add a coefficient of 2. I'll save those pure elements for last. And now I have 4 hydrogen on both sides. And I have 2 oxygen on both sides. It is balanced. Does anyone have any questions over that?
How do you get the two
Over here, to right here.
on the product?
The reason why we have two is if I multiply an H2O that already has, let's say, I have one H2O. There's only one oxygen. The only way for me to get it to be two is if I have to double the amount of those H2O. So that's why if once the second I put a two out front, I now have two H2O. And so the blue is, let's say the blue particle is the oxygen. How many are there? Yeah, so because I have assumed there's a one there, so 2 times 1, 2. Great question. So yeah, on the next slide, it asks you a question about coefficients. So I'm gonna write down that balance reaction because you work so hard, I'm not gonna have you memorize it. 2H2 plus O2 becomes 2H2O. Let's do the coefficients. What's the number of coefficients in front of H?
2,
2 oxygen,
1,
1, H2O,
2,
2. Okay, what is the sum of the coefficients of the whole balanced equation? So it's asking for everything. 5. So this question kind of summarizes this and this. And this is an excellent question, what you could see on the exam, because it says when hydrogen reacts with oxygen to make water. So you know I have to create this balance reaction, and then I need to add up all of the coefficients. That's why it's going to be C. So this combines those two, and you have to understand, okay, balance the reaction and then add them all up. What is the sum of the coefficients on the reactant side?
3,
3 on the left side. What is the sum on the product side?
2,
What is the coefficients for oxygen? Yeah, so this question, I could literally change up that front part of the question a bunch of different ways, and it'd still be a very similar question. But whatever I throw at you, because you know how to balance a reaction, you can answer it. And then sometimes they're nice and they will give you the balance reaction and have you answer it, but sometimes they're not so nice if the equation is super easy or super simple. Let's do this one after the mental break because it's 12:49. Have a mental break, come back at 12:55 if you need to go use the restroom or just go and stretch your legs. If you want to look at your worksheet, you're welcome to get a head start, but I will see y'all at 12:55. Let me pause this. All right, this one's gonna be a little bit more fun. I'm biased, I know, but this one is more fun and I'll prove why. Let's talk about butane. So reminder, you want to get comfortable with this little figure CN H2N plus 2. So when I say butane, how many carbons? C4H 10. So 2 times 4 plus is 10. So butane burns in air. When you think burns in air, it just means it combines with oxygen. If you were to just say air in general, there's just so many chemicals in the air. There's carbon dioxide, there's nitrogen gas, there's so much. But for combustion reactions, we focus on oxygen because think of fire. For fire to happen, you need oxygen. So burn, oxygen. It produces carbon dioxide and water. Let me put those boxes around because I want to make sure I don't touch what is inside these boxes. And this one will be a several step process, and that's why it makes it fun. It's a puzzle. First, let's count. On the left-hand side, carbon. 4, yes, there is a subscript in front of the 4, sorry, behind the 4. Carbon, right-hand side.
1,
1, so CO2, 1 carbon. Hydrogen, how many on the left-hand side? 10, there's only one that has hydrogen, and there are 10 of them. Right-hand side? 2, H2O, and there's only one of them so far, so that means there's 2. Oxygen on the left-hand side,
Two,
2 on the right-hand side.
three,
So in this compound, there are 2. In this compound, there is 1. I have to add them together because I'm asking for total. Okay, and that odd might make things a little tricky. I'm going to start with the carbon because to me, carbon's the easiest. I want my carbon on the right-hand side to be 4. So what do I have to do to make this 4? I have to put a 4 in front of the CO2. Now, that will change my carbon, but it also changes my oxygen. So what is my new total of oxygen? So I have 8 here, and I have 1 here. Does everyone see that? But by taking 4 CO2, 4 times 2 is 8. And then, yeah, so now I have 9 oxygen. I'm gonna save oxygen for the end because it's by itself as a pure substance, and that's usually easiest to play around with. So next, I'm going to pick hydrogen because my carbons are balanced. Hydrogen, on the left-hand side, I have 10. On the right-hand side, I have 2. What do I have to do to get this 2 to be a 10? I have to add a 5 out front because 5 times 2 is 10. But now I have a new number for oxygen. So I have 8. Now how many oxygen?
13.
Yeah, so 8 plus 5 is now 13. So good news, we have our carbon balance, we have our hydrogen balance, but our oxygen's not balanced. And this Dr. Patterson was talking about with those odd numbers being a little tricky. Because O2 is an even number and I would need to add 11 O2, I can't add odd numbers. Sometimes they are going to be necessary to get in the habit of writing it as fractions. I want to write it as whole numbers. So I add any number in front of oxygen to get it to be 11. I can't. Does everyone understand why I can't? So to make it better, I'm just going to multiply everything by 2. So if I put a 2 out front of here, if I put a 2 out front of here, so I'm taking the 1s, multiplying by 2. The 4, multiply it by 2. I now have 8. 5, multiply it by 2. Okay. The reason why I do that is I'm trying to get it in a way where I can add numbers in front of the oxygen to get it even. Okay. So let's now redo everything. How many carbon on the left side?
8.
How many carbon on the right-hand side? All right, are balanced. How many hydrogen on the left-hand side? 20. How many hydrogen on the right-hand side? So 10 times 2, 20. All right, on the left-hand side, how many oxygen? 2 times 2, I get 4. Right-hand side, let's break it down. For CO2, how many oxygen?
16.
8 times 2, I have 16 oxygen. And then 10 times 1, how many oxygen? So what is my total oxygen?
26.
26. Does everyone see how I was able to calculate my oxygen? And it's okay if you're not as fast on it, just take your time, add them up. Now, what is the difference between these two? How many oxygen?
22.
26 minus 4, I got 22. Because this is O2, let's divide that 22 by 2. What do I get? 11. So if I change this to an 11, wait, sorry. My bad. I jumped the gun. I have to add 11. I have to add, because I have the 22 difference. I have to add 11 O2 to what I have here. So this, to get it to 26, would be 13. I caught myself in that mistake because I took 11 and I multiplied it by 2 and I got 22. And that would mean that I would have 22 here, not 26. That's why I knew, okay, add 11, don't rewrite it 11. So Thanks for helping me catch my mistakes. All right, so I put a 13 out front. And now 13 times 2 is 26. I have 26 hydrogen on the left, and I have 26 oxygen on the left and the right. Okay, so if you have that odd number, and there's no way in hell you can actually put that odd number in there because it's a diatomic molecule, just multiply everything by 2, and then it makes it so much easier. So this is the balance reaction for a butane combustion reaction. So this was a lot more fun because we had to really challenge ourselves, and that's a good thing. You're not supposed to be able to look at it and say no. I couldn't even look at it. And then I Googled it to double check and make sure I was right because I didn't trust myself. And we're right. I double checked. Google is wonderful. As long as you're checking, you're not. So pro tip, occasionally, as you go back and forth on coefficients to balance an equation, you end up with a set of coefficients that could be reduced. Sometimes, let's say you multiply something by 3, and it could come to a smaller number. You always want to have the common denominator, the lowest common denominator be the answer. That only works if you can divide every number by the same number. You can't divide one and not the others. Otherwise, your equation is not considered correctly balanced. Here's an example. What's wrong here? Yeah. So this one, and this one, there is a common denominator, and that's 3. So if I divide all of them by 3, I would get N2 plus 3H2 becomes 2NH3. Both of these reactions are balanced, but the correct answer is the one that has the least, the smaller of the numbers. So predicting products of combustion. Sometimes it's not going to be so simple if your fuel is not just carbon and hydrogen. If it's just carbon and hydrogen, your products will always be carbon dioxide and water. But if you mix a different type of fuel in there, it might change your products. So the reactants, when I say I'm burning this fuel with air, it's always going to be burning with oxygen because that's what the burning requires, oxygen gas. So reactant will always be fuel plus O2. And the fuel will break up and combine with oxygen on both of those little parts. So the atoms in the fuel split apart and combine with oxygen to make products. So if my fuel, if I was to like do silicon is similar to carbon, but it's not, it's a different element. And like if I did silicon with any type of hydrogen, it would break up and the silicon would mix with oxygen and the hydrogen would mix up with oxygen in a very similar style as carbon. The fuel contains only carbon and hydrogen. The products will always be carbon dioxide and water. So any type of alkane. If the fuel contains a metal, the metal oxide will be formed. So magnesium. Yeah, balance it. So magnesium combined with oxygen will have a combustion reaction and will produce magnesium oxide. So metal plus oxygen. On the last slide, we were just going to predict. I don't want to take up the rest of class time to go through all this. So I'll do a few with you, and then I'll challenge you to do a couple on your own or work on the worksheet. But I do want to point out we already did D. D is the one we just did for butane because it's C4H10. So I'm just not going to include that one because we already did it. But you can practice it and see if you get the right answer. Let's do, what alkane is this? 3, propane. Yeah. So C3H8 plus O2, need a little bit more space. Becomes, okay, it's a hydrocarbon. So it's carbon and hydrogen mixed with oxygen. What are our products?
Water.
water and carbon dioxide. It is an always for an alkane. Let's count how many carbon on tin side.
Three.
How many carbon on the right? One. Hydrogen left. 8, hydrogen right. 2, and then oxygen left. Oxygen right. 3, okay. I always start with the carbon because it seems like that one's the forward. For me to get the carbon to be balanced, I need to put a 3 out front of the CO2. So now if I take out this one, I'll replace it with a 3. And then the oxygen will go from a 3, so I have 6 plus 1, I now have 7. So 3 times 2 is 6 plus 1 oxygen is 7. Next, I'm going to play around with hydrogen. So I'm going to change this 2 to 8. To do that, I need to put a 4 out front of the water because now I have 8 hydrogen. 4 times 2 is 8. But my oxygen is going to change too. So I have 6 plus 4, and that gives me 10. Ooh, even number. That's a good thing because now I don't have to multiply the whole reaction by anything. So if I want to have this be 10 oxygen, what number am I going to put out front? 5. And we are done. That is the balance reaction for propane. Y'all do the next one. But first, tell me, what is the name of this alkane? Pentane. C5, pent. But y'all go ahead. I'll fix up my letters and stuff and I'll put up some answers. But y'all practice with number B by yourself to see if you're able to do it. I have answers in front of you, but I just want, one, write them down and challenge yourself, see if you're able to get them. I want to move on to the activity for the main part next, because I want to have enough time to go over some of the past exams. But when you get a little downtime and you need to practice this or study for the exam, definitely check your answers with mine and see if you get the right answer. So if you did B already, you should get an 8 in front of the O2, a 5 in front of the CO2, and a 6 in front of the H2O. C is gonna be just like D, where we had to multiply the whole reaction by 2, because that one, you had to get an even number. So that one's a tricky one. D is also tricky. And then E, this is a hydrocarbon. They didn't add an O here, but it still breaks up to make oxygen, and this is the balance reaction. So if you want to take a note of what the right answers are and compare it, or check and see if my answers are right, you never know. But right now I'm gonna ask everyone to switch over to the worksheet. If you are online, the sheet is available to you under modules. I do not have a key yet. A key today. So I'm gonna make the key today, and I'm gonna post it online so y'all have access to it. Just know it's not available right now. But yeah, open up that worksheet, start working on it. We'll do that for a little bit, and then at maybe the last 10 or 20 minutes, we will switch over to the exam.
Yeah.
But you still be.
Okay, yeah, I'll do it, so.
Since we have some time before the exam, I don't want to do this the day of the exam. We'll definitely have some time to review some questions before the exam, but I especially need to go through some things before the exam. But first, I want to point out the exam will be closed notes, closed books. The only thing I will provide for you is a blank periodic table of elements. The exact one is in our resources tab. So it'll just say exam periodic table of elements. That's the only thing you're given. So you will not be given a periodic table that tells you what's the halogens, alkali earth metals. You won't be given a table that says these are the metalloids. It just won't happen. That's not going to be provided for you. So the nomenclature little cheat sheet I gave you will not be provided for you. So it's just going to be periodic table of elements and the exam. It never hurts to ask. I'd rather you ask than not ask. I'd rather you just think, okay, I'm alone in this. You're not alone. My job is to help you. It just keeps turning off. That's the problem. Okay. Turn. Maybe it's just not happy. Perfect. All right. You are allowed a pen or pencil and razors and a calculator. Reminder, no graphing calculators, just this type of calculator. I will have extras, but you cannot use a graphing calculator. Yeah. Remove your hats and turn them around, just because we've had students cheat before by putting things here in the brim. So I'm gonna have you turn your hats around. Remove earbuds, can't have earbuds for the exam. I understand that some students do really well with certain accommodations, but the only way you can have those accommodations is if you schedule your exam through the testing center. So if you have accommodations and you want to take the exam using your accommodations, use the ODS testing center. But we can't have your phones in or, the noise canceling stuff. We can't do that because I can't confirm what's going on. No cell phones. Cell phones are not calculators. If you have to use a restroom, you are entitled to pee. I'm not gonna tell an adult they can't use a restroom, but usually I'll be like, show me your cell phone. I'll make you put it on your desk or put it away, and then you can go use the restroom. But yeah, that's the big thing about that. Once the exam begins, you can't share or borrow from anyone. The number of multiple choice might change. I don't know what I'm doing yet. My goal is to potentially start our exam around maybe 12:40, maybe 12:35-ish. We'll get started and do like 30 minutes of practice problems, and then we'll start the exam. Yeah, if I observe cheating, I'll remove a student anytime. We're not gonna do Scantron sheets. There's only 26 of you, so I'll just have you write everything on the exam itself and I'll grade it within the day. For the short answer problem of the exam, write as much as you possibly can. I love partial, but the worst is when students panic and don't do anything. I'd rather you do a bunch of mush where I can give you a couple points than do nothing. So please, please, please write as much as you can. And then have your Texas State ID ready when you come in so I can confirm you are who's taking the exam. Okay. Before I go over some practice problems, I want to point out, I gave you two documents. You have exam 1 and exam 2. This is from fall of 2024 resources. Exam 1, go to the last page. Number 1, make a note. This is not going to be asked of you. So this is exam 11, combustion. This first problem is not going to be asked of you. So don't worry about knowing it for this exam. Okay, that's the only problem on this exam that will not be asked of you. For exam 2, everything that you see a green highlight could be asked of you. So for page 1, every problem could be asked on the exam. So if you want to make a note or circle the numbers that you want to study. You have to study 1 through 8 on page 1. Page 2. Ten, 11, 13, and 16. Does everyone have that? On page 3, 19, 21, and 27 and 28. And then none on the last page of the multiple choice. So I'll skip right now to only the free response numbers 1 and 2. None, not 3 or 4, just 1 and 2. All right, so that's the only ones that might be expected of you. So while you're studying, I recommend, this is the way that I learned to study. To really challenge you and see how you would do in the exam. Practice the exam with just an empty periodic table balance, no notes. And then see what questions you can answer correctly, because the answers are also available to you out there. See what you're good at, and then see what you're not good at. Then study up on what you're not good at, and then practice those questions without any notes again. If you practice the exam with your notes, and you come in and take the exam, it's not going to be good. because you rely on your notes to get the right answer, and you will not be having your notes for the exam. So the way that this is why I'm saying get all the homeworks and the quizzes out the way, because the true way to study for the exam is to practice without your notes. See if you can do those worksheets without your notes. See if you can do our slides again without your notes. That's how you truly get more comfortable with it. And if you can answer majority of the questions without any assistance correctly, then that tells you you are ready to do a higher, the grade that you want. So that's the way that you study for these ones. So let's get into it. We have 8 minutes, but I will stay late. If you are willing to stay late with me, I will stay late and keep going. Okay. Let's go back to exam 1. The one with all of the questions. And I'm gonna work with y'all. I want y'all to help me answer these problems. All right. I like this question. Compare the numerical prefixes for naming alkanes and binary molecular covalent compounds. Some of prefixes are very similar and some are very different. Which number has a very different prefix when you are naming an alkane versus when you are naming a molecular covalent compound? This is a question you definitely want to use elimination, because if you don't have it memorized, you want to use your elimination. So remember how I said after 5 or after 4, it's easy. So for both binary and alkanes, it's penta, hexa, hepta, octa, nona, deca. Those are easy. So I'm not talking about those. So any of these answers that include penta through deca cannot be the right answer. Does that make sense? Which means it doesn't even matter if you remember the answer. You have the answer. So this is why I'm saying use elimination tactics, because if you don't have it memorized, you can still get the right answer. And if you are comfortable, so for alkanes, this is what I'm talking about. They're the same after tetra and butyl, but before then they're different. So for alkanes, it's for covalent, it would be mono. So you can see how they're drastically different. And that's a great question, because I'm testing to see, okay, can you eliminate or do you have it memorized? Okay. So how do you about that? All right, these questions are really good because it also tests how confident you are with your knowledge. Let me just circle this and put A. Think about the procedure to name binary molecular covalent mol. So this procedure, we're not in